All right, today we're going to start a series of what we call chi-square tests. And there's three that we're going to look at, but we're just going to do the first one today. The first is called the goodness of fit tests. Then we have the test for independence. And last but not least, we have homogeneity of proportions. Homogeneity, I believe I spelled that right. Okay, so this chapter consists of these three hypothesis tests: goodness of fit, test for independence, and homogeneity of proportions. And they all come under chi-square test because it utilizes the chi-square distribution, which we're familiar with. These two kind of go together because they have the exact same way of doing the critical value and test value. And the goodness of fit is a little bit different, so you want to separate that from the other two. Okay, so let's start today where we'll just do the goodness of fit test. Okay, so the goodness of fit test is used to determine basically how good something fits, right? So it's called goodness of fit because we're trying to determine how good something fits. So what I'm going to write here is use to test whether a frequency distribution fits a specific pattern. To determine if a frequency distribution fits this hypothesized pattern. Okay? Now, in all of the chi-square tests, we have this O variable, and we have this E variable. So it's very important that we know what the O and the E stand for. The O is going to be representative of observed frequency. Okay, at this frequency. And E is going to be expected frequency. So with each of these chi-square tests, we have this O, which is observed, so that actually happened. Okay, that was actually observed, that actually happened in our sample. E is what our hypothesized expectation is. Okay, so it's very important that you know the difference between O and E. O is observed, that actually happened. E was our expected pattern. Okay, good. So anytime I do a new hypothesis test, I have to tell you obviously what distribution it uses, and this is going to be a chi-square distribution. For the goodness of fit test, all the tests are right-tailed. Okay, so whatever alpha is, we're going to put it in the right tail. So right tail. With the chi-square test, we have a degrees of freedom. Okay, this degrees of freedom is k minus 1, not n minus 1. And k stands for the number of categories. Okay? So for this test, the degrees of freedom is k minus 1, and k is categories. All right, and then finally, what's the test value formula look like? It looks like this. And again, you have to have those O's and E's down. So it's summation, and I'm just going to put a big parentheses because this all is being summed. You have O minus E, quantity squared, divided by E. And we're summing that thing several times. Okay? So it's O minus E, quantity squared, divided by E. That is my test value formula. So it's chi-square distribution, right tail, just put all of alpha in the right tail. The degrees of freedom is k minus 1, k is categories. And my test value is the summation. I'm going to add up a bunch of things. O minus E squared over E. We're just going to add that piece several times, however many k's there are. Okay? Okay, let's take a look at an example here. So the first example I have, a children's raincoat manufacturer wants to know whether customers prefer any specific color over other colors in children's raincoats. He selects a random sample of 50 raincoats sold and notes the colors. The data is shown. At alpha equals 0.10, is there a color preference for the raincoats? Okay, so here's our question. Example 1. At alpha equals 0.10, is there a color preference? In raincoats. Okay, so we have this manufacturer. He's trying to determine if there is a color preference. And then he observed 50 people and saw what color they bought. So we have yellow, we have red, green, and blue. Okay, so there were 50 raincoats sold, and this is the distribution, 17, 13, 8, and 12. Okay, so let's start this test. This is a goodness of fit test. So if we don't have an expectation, we don't know the color preference here, then we kind of say, well, we expect the color to be the same, right? That's kind of our normal stance. Well, if you're going to show me that there is a preference in color, that's tending to be the alternative hypothesis. But our null hypothesis is that there's probably no preference and that colors are preferred equally likely, okay? So what's a little bit weird starting in this chapter is our HO and H1s are kind of more descriptive as opposed to just mu equals 5, mu not equals 5, okay? So for this one, our HO and H1 is going to be something like this. No color preference versus there is a color preference. Okay, and a lot of these descriptive ones, our normal outlook is if you're going to show that there is a color preference, you're going to have to show me that in H1. Okay, HO, we're just going to say there's not. That's step 1. Okay, great. Brings us to step 2, critical values. I told you it's always a right tail test. So go to your chi-square distribution, go to the right tail. And we said alpha was 0.10 here. And what would my degrees of freedom for this one be? 3, right? We had 4 colors for the categories, and 4 minus 1 is 3. All right, so let's look up this value. 3 degrees of freedom, 0.10 in the right tail. And remember, our alpha is in the right tail, so this is really set up perfectly. Just look at 0.10, and you should get 6.251. Great, and that brings us to step 3. Okay? Now, again, my test value is kind of weird. It looks like this. Chi squared equals a big summation O minus E quantity squared over E. And put this whole thing in brackets, because that whole thing is being added several times. Okay, so I go to each raincoat. I'm going to have yellow, I'm going to have red, green, and blue. These values are my observed values. Those actually happened. 17 yellow raincoats were bought. 13 red ones were bought, okay? So the question is, what was my expectation? So my expectation was there's no color preference. So if there was no color preference, then how many should have been bought? How do I figure that out, right? Well, if there's 50 raincoats sold and they all should be the same, how am I going to figure out that number? Does everybody understand the question? So there's 50 total raincoats sold, right? So there's 50. And if they're all supposed to be the same, I would just do 50 divided by 4, right? And that would give me 12 and a half. Okay, so again, to repeat what just happened there, O is the observed values. That was actually happened. This is what actually happened. Our expectation, if there was no color preference, it'd all be the same, okay? But it also has to add up to the 50 raincoats. So it's 50 divided by 4, which is 12 and a half. Okay, great. If you can understand that, then you're ready to go. So we start with yellow. We observed 17 yellow. We expected 12.5 yellow squared divided by 12.5. Plus, then you move to red, okay? So it's O minus E squared over E. 17 minus 12.5 squared over 12.5. Then move to red. How many observed red did we have? 13 minus 12.5 squared over 12.5. Plus, move to green. We observed 8 green, so it's 8 minus 12.5 quantity squared over 12.5. That's a 12.5. And then finally blue, we observed 12 blue, so it's 12 minus 12.5 quantity squared over 12.5. Okay? You should definitely get a positive answer because if this is negative or positive, regardless, you're going to square it. So it should be positive. So you should have a positive plus a positive plus a positive plus a positive. Okay. Go ahead and spend a couple minutes on your calculator and add that up. And let's see what we get. Make sure to use parentheses, otherwise you will not get it right.
This is 11.1 chi-square test. 11.1? For goodness of fit.
Okay, I added it up and I got 3.28. So see if you get 3.28. So double check that for me. Okay, great. Going back to step 2, 3.28 is not in my right-tailed critical region. So my test value doesn't fall in the region. So I'm going to not reject HO, and I'm going to say there's no color preference. So step 4, do not reject HO. And step 5, no color preference. So continue to buy all the colors of raincoats. Okay? If you're the manufacturer. So again, this test is we're trying to determine how good something fits some pattern, okay? Questions on that one? Okay, good. Let's look at one where there is a specific pattern that is believed or hypothesized, and let's see if we fit that pattern. So let's do another example. Okay, the dean of a college hypothesizes that final grades in his department will be 40% A's, 30% B's, 20% C's, 5% D's, and 5% F's. At the end of the semester, the following grades were recorded. For alpha equals 0.05, is the grade distribution different than what was expected? Okay, so let's take a look at this one. Example 2. The dean believes grades will be 40% A's, 30% B, 20% C, and 5F, 5D. Okay? So the dean believes that this will be the distribution. Here's what actually happened. So we had 45 A's, we had 52 B's, we had 39 C's, 8 D's, and 6 F's. Okay? And we looked at, that's a total of 150 grades. Okay, great. And then it says, at alpha equals 0.05, testing claim. At alpha equals 0.05, test his claim. Okay, so this is a little bit different from the last example. The manufacturer wasn't sure, didn't have a color preference. So the expectation was there's no color preference, and then let's test if there is. This one, the dean actually believes this will be the grade distribution, okay? So this is similar to an HO equals, right? If the claim is blah, blah, blah equals this, that's our HO, okay? So this will be the HO, the dean's belief, okay? So step one, HOH1. Grades distributed as dean's claim. Grades not distributed as dean has claimed. Okay, and it's very similar to an equals not equals, with the HO is always going to have the equal sign. Okay, great. And again, notice it's very descriptive today, right? It's a lot more descriptive than in previous examples. Okay, you guys go ahead and move on to step 2. Tell me what the critical value is. It's a right-tailed test, chi-square distribution, alpha is 0.05. And categories, we have A, B, C, D, F. So there's 5. So the degrees of freedom will be 4. So our right-tailed test, alpha is 0.05. Degrees of freedom is 4. Should only take a minute to look that up because our chi-square table is set up for right-tailed area. And what do you guys get? 9.488, right? 9.488. Great. Moving on to step 3, test value. Okay, this one's going to take a little bit of time. So let's go back and recap a couple of things. With the test value formula, you need O and E for each category, right? These are my O's right here. The actual data is your O's. Those are the observed frequencies. What's my expected frequency on this problem?
Well, percentages?
Yeah, so if there's 150 people, and he expected 40% of them to be A's, you're going to do 40% of 150, and that would be the dean's expectation for A's, okay? So let me just sneak it up here. Let's do the expectation. So 40% A's, you're going to do, in your calculator, do 0.4 times 150, and what do you get? 60, great. So the dean expected there to be 60 A's, okay? Moving to the next one, you have 30%. He expected 30% of the 150 to be B's. So do 0.3 times 150, and you get 45. So the dean expected 45. Okay, and keep going. So 0.2 times 150, expected 30 C's. And then 0.05 times 150, expected 7.5 D's. And also 7.5x. So these were the expected values. These are the observed values. Please don't mix those up. The observed values were actually given in the data. That actually happened, okay? All right, you guys got some work to do. So this test value is going to be 60 minus 45 squared divided by 60, right? Plus 52 minus 45 squared divided by 45, right? Plus, plus, plus. So you have to do all of those, okay? So go ahead and get on that and tell me what you get. O minus E squared over E, and sum those all up. 45 minus 60 squared over 60 plus Got to go to each grade. (52 minus 45) squared over 45. I'm just going to cheat and put plus dot 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 and go to the last one. 6 minus 7.5 squared over 7. Okay, let's add these up. It's going to take a couple minutes here. Okay, about 7.872. Is that what you guys got? Approximately 7.872. So just be really careful. I'm actually typing it in just this way. Parentheses 45 minus 60, parentheses squared, divide by 60, plus parentheses, on and on and on. And I got 7.872, which again, not quite big enough to be in my right-tailed area. So step 4, do not reject HO. And step 5, we agree with Dean, right? Because in this case, it was like an equal situation, and the Dean's hypothesis was the HO, so we're going with the Dean's plane. Questions on this problem? So what we did today was goodness of fit. The next time we're going to do test for independence and homogeneity of proportions. Okay, and that'll be the end of chi-square distribution. Then we'll move on to the other stuff. Questions on this one? Yes?
How did you determine which on the HO, H1, which one was going to be his claim?
Right, so it's very similar to in the previous couple of chapters. If you had Dean believes, will be, it's like equals to, right? And equals to is always HO. So it's that type of thinking.
Okay.
Okay? Other questions? All right.